So we're looking at the practice final here. The table is going to be used for first bunch of problems. Represents total points throughout the entire careers of Daniel and Henrik Sedin. All right, so NHL players, hockey players. All right, so the first question says a player is entering the NHL has a profile that matches that of Henrik, and we want to know the probability that that player would earn at least 50 points in any given year. All right, so we're going to treat Henrik's career as a population, find the mean and the standard deviation. We're looking for the probability that the total points would be at least 50. So this is going to be a norm CDF situation. All right, so we can do norm CDF, but norm CDF gives the area to the left of a particular value. So if we're going to the right, we want to do 1 minus. All right, the benchmark value is 50, but then it asks for the mean and the standard deviation. All right, so let's go to the calculator. Under statistics, we type in the information. I already did this in advance. I put Daniel Sedin stuff in V1N1, and I put Henrik's point totals in V2N2. All right, so if I go to stats, go over to the V2N2, find the mu, which is 62.941. And the standard deviation sigma, 22.467. If we pop this into the calculator in the calculation app, so 1 minus toolbox, we go to probability, distributions, normal. I'm going to put in the 50. I'm going to put in the population mean and the population standard deviation. I'm going to hit OK, and it gives me a probability. The closest one that I have here is 0.718. All right. For the second question, which of the following is the mean of the points total for Daniel Sedin, the population standard deviation for Henrik, and correct statement regarding unusual values. So let's see if we can eliminate some things here. Again, in the statistics menu. So Daniel is the V1N1. So the mean is 61.235. So we kind of looked into it. So it's got to be this one, because that's the only one that has a mean of 61.235. But let's just verify the rest of it. Standard deviation for Henrik, so that's this number. We already figured that out, is 22.467. So we're good there. And then the statement about usual versus unusual values for both of them. I'll just give you the rule here. That's going to be mu plus or minus 2 sigma. That'll determine the usual or unusual values. You run these numbers, any number that from the table that falls outside of the intervals that you create for both Henrik and Daniel would be considered unusual, right? But in this case, it ended up being irrelevant because we were kind of locked into the second choice based off of the population mean for Daniel Sedin. All right, now this is a four-parter. It's not multiple choice. Say find each. We have probability of 2006 given that you're working with Daniel. I'm going to get some equal signs here. So in the Daniel group, so that's all this stuff, we're looking for 2006. So that would be this value out of the total for Daniel, which we don't have, but we can get fairly easily. Because if you go into your stats app, look for the one that says the sum of values, you get your totals. So 1041 for Daniel and 1070 for Henrik. So 84 out of that 1041. So that's that first value. Daniel given the year is 2006. So now we're going this way. The total value for that row is 165. So 84 out of the 165 is what we're looking for here. So 84 out of the 165. 2006 given Henrik. So we're looking at the same general process. So for Henrik, 81 out of 1070. And then 81. It's the same row as Daniel given 2006. So 81 out of 165. All right, the next one's asking us for the equation of the line of best fit and also to make a prediction. So what we would do here is go into the regression app. I also type the data here, so kind of ahead of the game. Go to graph. You have the scatter plot plotted. Go to regression. Linear, the second linear option is what we're going for. It'll plot it. And then if you hit the down arrow, it'll bring up the equation of the line of best fit. You could also go into regression itself and do it. You might consider doing that only because we do have to make a prediction, but you can get it like this. Now, some of the choices have the X value first, so just be careful. You know, I don't want to say it's a trick question. It's just one of those where you just got to kind of keep your eyes open. All right. So that first choice, it's in a different order, but that first choice seems to be what we're looking for. The X value is attached to the 0.985, and then we have a 2.606. So that looks like our winner. And it's another one of those where that second part didn't seem to be relevant based off the fact that the first part was kind of locked in. But let's do it anyway. If we scroll down, you'll see predict Y given X and find X given predicted Y. Now, the second part to this question was, based on this answer, what point total would you expect Henrik to get if Daniel earned 90? So Henrik is my Y column. Daniel is my X column. So it's saying if X is 90, what's Y? So I'm just going to put in a 90 for X. Confirm. And that little Y hat value, so you have X equals 90, you have Y hat equals 91.283. That confirms this value here. So we're in good shape. Box plot is created for the total points of Henrik throughout his career. All right, so again, that's my second data set. But I'll go into statistics, go to graph, box plot. It'll plot them both. The first one is Daniel, the second one is Henrik, and we're looking for Henrik. The 5-number summary are the important values that make up the box plot. So these 5 values, you see that it's changing at the bottom of the screen. Minimum 29. All right, so it's looking like it's this choice. Just confirm it. The second value, 43.5, 55, 81, and 112. So that is confirmed. All right. Now this question is really just talking about the design of the experiment. Observational study. Sports enthusiast claims that he could take any 5-year period from the careers of Daniel and Henrik and prove that Henrik is a better player. To prove his claim, he designed an observational study. How might he have designed the study? All right. The individuals in the study, we're talking about the years in the career of each of the players. So don't be fooled. Like Henrik is a person, Daniel is a person. That sounds like what an individual would be defined as, but individuals are specific data points. All right. So the individuals here would be points in any year. All right. Any variables? All right. So we're trying to show that Henrik is a better player. Now, if Henrik is a better player, that one way to prove that or justify that would be to say that he earned more points. All right. So the variables here would be points earned. By year. So it's really the same thing. All right. So we have a variable that represents the change in time, so years, and then we also have the points that are earned. Right. Since there's only the 2 players, I mean, you could define each player as a variable, but since we're only comparing the two players, there isn't much variation there. It's just you're either Daniel or you're Henrik, so we're not really looking at that. Points earned is really what we would call the explanatory. Time would be the explanatory variable, and points earned would be the response if it were an experiment, but this is an observational study. Factors that could affect the variables, right? So they might end up being lurking variables. Injuries, just give me at least two on this. Injuries, age, so that would be the time component. Any of these that are not under control would be a possible lurking variable, could cause confounding in the study. Skill level. I'm trying to keep it generally vague because I don't expect people to be experts in hockey, and maybe your sport is soccer. Maybe you don't have a sport, but you can kind of relate to a lot of these things. Like if you're a musician, who's the better musician? A lot of variables go into that, but I would imagine skill would be one of those things. We could also probably say things like, like what position you play. And even just like tying that to like a orchestra, if you're going in the music realm, you could say if you play the violin, you're going to be measured. Your skill is going to be measured differently than if you play the oboe, or the drums, or the cello. So it should be a fairly universal approach to solving these problems. State a reasonable income. Outcome of this study. We could say that Henrik is a better player, so Daniel is not as good as Henrik. Oh, actually, the equal sign there would make it that he could be as good. Henrik. Is that spelling his name right? No, there's no C in Henrik. All right, we could say that they're the same. I don't know why I opted to go lowercase here, but there's no particular reason for that. Or Daniel is better than Henrik. So I'm kind of going the bullet points route here. I'm not asking you to go too crazy in terms of your answer. All right, just kind of give me the highlights. Should randomization be used here? Why or why not? You can make a case in certain situations that randomization is not completely necessary, but in this case it would be. So yes, because depending on the 5-year span, different conclusions can be determined or arrived at. All right, and really the idea behind that statement is, I can, if I have liberty to choose any 5-year period, if I wanted to prove that Henrik is a better player, I would just take the worst 5 years from Daniel and the best 5 years from Henrik and compare those two. Right. So if I'm left to do that, then I could arrive at whatever conclusion I want. Right. Unless the values are so close to one another, which is actually the reason why I chose Daniel and Henrik Sedin. Their career paths were very, very similar. Randomization should be used to take away that intentional bias. All right. Next one, at the 5% level, test the claim that there's no significant difference in population mean points earned over the career spans of Henrik and Daniel. All right, so I'm going to go back and I'm going to go into statistics. I'm going to grab their relevant information. All right. So here we're going to treat their means and standard deviation as samples because it made that assumption, or told us to make the assumption. Assume that distributions of points are samples from population of points by any NHL player. So we have, oops, sorry, that jumped on me. We have Daniel Sedin, we have Henrik Sedin. We're going to have a mean for Daniel, 61.235. A mean for Henrik, 62.941. Sample standard deviation, 21.513. For Henrik, 23.158. All right, the N value is the number of data points, 17 for both. Oop, I don't know why that happened. I do know why that happened. All right, just fixing that. All right, so Daniel will be my first set of data points, so they get subscripts of 1. Summary statistics. So my hypotheses, null and alternative, would be that there is no difference. That means they're equal. Or that there is some difference. I don't know which direction, but based off of these values, you might opt to go with a less than. All right, because it seems like Daniel has lower values than Henrik, but you could also just simply go with a not equal and make it a two-tailed test. All right, so I'm going to draw my graph. We're assuming that we don't know the population parameters, so this is going to be a 2-sample t-test. So left side, right side. The degrees of freedom are always going to be for a 2-sample, well, not always, but for the kind that we learned about, the degrees of freedom is whatever the smaller n value is, minus 1. In this case, they're the same. So 17 minus 1, 16. All right, we need some critical t values. So let me get out of here and grab those. So we go into the toolbox. We're going to do students t, inverse t. They said 5% level, so alpha is 0.05. With 16 degrees of freedom. So we're looking at negative 1.746 and positive 1.746. Oops, apologies, sorry. It is two-tailed, so this should be 0.025. And then I hit that for some reason. All right, so this is 0.025 because between the two of them, it has to add to 0.05. So we split it if it's two-tailed. So this is negative 2.120, positive 2.120. We need the p-value and the test statistic. So in my inference app, under tests, 2 means, t-test, we're going for the not equals. We put in our values. We have a fair amount of typing to do. 61.235, 21.513, 17, 62.941, 23.158, 17.05. Next, we have the p-value, which is 0.825, and the test statistic negative 0.223. So t equals. All right. So in either instance, we're not going to reject the null hypothesis. So the null is the keeper. Alternative goes away. And that's because if I were to plot my test statistic, it'd be somewhere over here. So say TS. All right. It's nowhere near the shaded area. And that even might be a stretch. It's probably closer to that middle. But the p-value, in order to reject the null, the p-value has to be less than the alpha value, and that's not the case. Right? So we don't reject the null. There is a formula that computes degrees of freedom, but we just go with the smaller of the n values, -1. All right, we go to next. You get a look at the picture. All right, it should kind of confirm what we already know. And then we just write up our conclusion. There is insufficient evidence to reject the claim that there is no difference in population mean points between Daniel Sedin and Henrik Sedin at the 0.05 significance level. Now, the second sentence of the conclusion, the template, would address the alternative hypothesis, but they asked us to just test a claim that there is no significant difference, which we actually already addressed in the first sentence, so that's all we'd have to write in our conclusion. All right, so that first bunch of questions, 1, 2, 3, 4, 5, 6, 7 questions. I think I said first 6 questions, but the first 7 questions on the final will be related to a table. So structured very similarly to what you see here. Then we move on to more general types of questions. If you're presented with a question that requires you to compute the probability of an event occurring, given that another event has already occurred, that's conditional probability. What formula would you use? This is the formula for conditional probability, or at least it's one variation of that formula. This formula here is the addition rule for non-mutually exclusive. This is the addition rule for mutually exclusive. All right. When I say mutually exclusive, I mean no overlap. The non-mutually exclusive would be the opposite of that. Right? So this is the multiplication rule for independent events. And I'll just throw in here, if we have probability of A intersect B is equal to the probability of A times the probability of B given A, that's the multiplication rule for dependent events. It kind of seems silly to not include that. Which of the following is not a necessary condition for a distribution to be considered binomial? Well, the 4 conditions are fixed number of trials, fixed probability, independent events, and 2 outcomes. All right, so fixed number of trials, well, they said variable number of trials, so that's not a condition. Fixed probability, so that's good. Independent events, so this one is not correct. And 2 outcomes, well, the last one is 2 outcomes, so we're good. All right, a randomizer makes 5 selections from the letters in the word muffle without replacement. So we want to know how many different 5-letter arrangements are possible. All right, 1, 2, 3, 4, 5, 6 letters are available. So what we want to do here is we take our 5 unique letters. Well, I'll sort of categorize it, just to try to keep it as organized as possible. All right, so the one thing you don't want to do is just type in a 6 factorial. And you could see, unfortunately, because of the nature of multiple choice questions, you type that in, it's actually a choice. So that's dangerous. All right. So just be careful about that. One, because we're only using 5 letters, and two, because there is a repeated F in there that would have to be accounted for. And in fact, just to kind of cover this, if I were using all 6 letters, then I would say 6 factorial divided by 2 factorial. Six factorial divided by 2 factorial to account for the different ways in which the letters F and F could be arranged, right? But here again, it's saying we're only using 5 letters. So our possibilities are, and I'll write no repeated F. All right. So it's kind of like we're taking the word muffle and just ditching one of the F's. All right. And then we have repeated F's. All right. So if there are repeated F's, then one of the other letters has to go. All right. So it could be MUFF L. All right. It could be, so I just ditched the E at the end. It could be MUFFE, ditching the L. MFFLE, ditching the U. And then UFFLE, ditching the M. All right. So here, it's just 5 factorial. Here, it's 5 factorial divided by 2 factorial because the F's are included in there, and you could rearrange the F's. If this is my first F and this is my second F, another word that I could actually write would be MUFFL, where I just simply swap the 2 F's. But that's the same word. MUFFL, nothing changed there. So we divide out the 2 factorial to account for that. All right, so this is 120. This is 120 over 2, which is 60. And that happens in 4 different ways. So I'm going to multiply that by 4. So that's 240. So I have 240 and 120. All right, so that's going to give me, when I add those together, because I could have the no repeated F's and the repeated F's, it's actually coincidentally going to give me a 360. I'm sorry, I don't know why I wrote 360 there. 240. So that really is just a coincidence. When we did the 6 factorial over 2 factorial, it worked out the same way. Please believe me, that really is just a coincidence. All right. But this takes into account that we had 5 letters with 2 repeats, and it happened 4 different ways. So that's why we multiplied by the 4. And also, I'm just realizing that my practice test form didn't update when I put the edits in, or at least I forgot to possibly put an edit. This actually should be the choice 360. All right, so I'll fix that online too. All right. I'm not sure where this stuff came. Oh, you know what? This was from the old version of the practice finals. This is actually the last question. This is the 10th question. So that would be it. I'm going to make the edits here to get rid of this stuff because that shouldn't be there. I changed that from previous semesters.